Students, so in this class I discuss magnetic flux density, uniform magnetic field and non-uniform magnetic field. So magnetic flux density is a number of magnetic field lines crossing unit area kept normal to the direction of line of force. So the direction of line of force means that is magnetic force. So number of magnetic lines passing through the given area, that given area is kept normal to the direction of line of force. This is the direction of line of force. So magnetic field, then area A. So the magnetic number of magnetic field lines crossing per unit area kept normal to the direction of line of force. So unit is Weber meter power minus 2. So magnetic flux density is a vector. Then uniform electric field. So uniform electric field means it's uniform, it's similar. So I have example for uniform magnetic field is earth magnetic field. So direction and magnitude. So direction and magnitude is constant, means uniform magnetic. So same direction all the magnetic lines. So all the magnetic lines have the same magnitude, so same value of magnetic field. So both magnitude and direction is constant is uniform magnetic field. Then non-uniform magnetic field. So non-uniform magnetic field, example bar magnet. So take a compass, that is a magnetic compass. So place it near the north pole. So north pole and north pole reflects. So north pole, so that arrow mark. So this arrow mark is north. So that tail, this is head, tail. So tail is south. So south and north attracts. So at this point, so here the magnetic compass needle direction changes. So the north and south attracts. So it's similar. So direction and magnetic field changes. See first diagram. So same direction. Here direction is constant. Second diagram. So direction is not constant. So one is going upward and downward, upward and downward, upward and downward. So direction is not constant. Here both direction and magnitude is non-constant. So here, so that is the direction of magnetic field in this direction, but it goes upward and downward, upward and downward. Then what is the magnitude? So what is the magnitude of magnetic field B? So for this line, compare these two lines. The value of magnitude of magnetic field varies. So these are non-uniform magnetic field. And final one. So what is the magnetic flux emanating from the magnetic dipole? So magnetic dipole means that is a bar magnet. So the bar magnet, from the bar magnet, what is the total magnetic flux emanating from the closed surface? So the magnet is placed in a, consider a closed surface. So the magnetic flux formula, if it is a non-uniform, so from the bar magnet we will get a non-uniform magnetic field. So closed integral B dot dA is equal to 0. So why is it equal to 0 means, since no isolated magnetic pole. So what is my magnetic flux? So number of magnetic field lines crossing through the given area. So from this, so we need to have a monopole. So from the monopole, so it's not possible. So if you break a magnet into two, so north and south, again it becomes north and south. So again if you break, we'll get again north and south. So we can't produce a single pole or monopole. So in magnets it is always a dipole. So monopole doesn't exist. So since no isolated magnetic pole exists, so the integral is always 0. So they may ask in 1 marks. So in this class we have discussed magnetic flux density and uniform magnetic field and non-uniform magnetic field. Then, so what is the total magnetic flux emanating from the magnetic dipole, that is bar magnets. So that is always 0 because magnetic monopole doesn't exist. Okay students.